Oh, nice. Can you hear me now? Yes, thank you. Yes, maybe I accidentally touched the button. All right, so we're going to study the surface of constant Gaussian curvature. Right. We'll begin with unit speed curve, right, in the XY plane. And so unit speed means this is going to be 1, right? F prime u square plus g prime u square equals 1. So if F prime u is determined, g prime u will be also determined. Okay. But essentially, you only have one functions here. So you look, the surface erosion is generated by rotating this curve in the XZ plane. Right, so the standard surface patch will be given by f of u cosine v, f of u sine v, and g of u. Okay, the v is the angle actually. V is the angle. Okay, when v is 0, this is the angle. This is the angle. So we are talking about this point here. Okay. Right. We find out the first fundamental form and the second fundamental form, and you're using that, we get the principal curvatures, and we use the formula in the book. There is a formula, okay, about the curvatures, okay, principal curvatures, and the sum of the the Gauss curve. So you have so you have first fundamental form, right, using this surface patch, right? So you get I is going to be e, in the book they use a du square to f du dv plus g dv square. Okay, the second fundamental form is m du square to that's L. Okay, so LMN. Okay, L M N. Okay, now for this particular example, okay, we find out, we can determine the coefficients E, F, G, L, M, N. Okay. We learned the formula. The principal curvature is completely determined by this the principal curvature. Are the roots of the following matrix, right? So actually is a difference of the two matrices, LM, MN minus K. This is a EFFG. Okay, so determinant of that going to be 0. Okay, the Gaussian curvature is going to be K1 times K2. Okay, and it's also given by so there's two formulas here. So after you simplify it, K1, K2, so that will be L n minus m squared, and here's EG minus f squared. So we're going to focus on this. Okay, that's a Gauss curvature. Okay, now in the last chapter, we're going to show that this actually is independent. This only depends on EFG and the partial derivatives, but it's not clear here. Okay, so that is Gauss's contribution. Okay, that's why it's called the Gaussian curvature. Okay. So in chapter 10, that's what we're going to start. All right, so this is a formula. Now for the surface of erosion, Okay, we have the formula. Okay, we actually, this is example 8.1.4 in the book. I also did the computation. So here at the very beginning for the surface revolution and the Gaussian curvature, because EFG, right? After you compute it, the EFG, E is going to be 1, F is going to be 0, G is going to be F squared. It's very simple, right? L is going to be F prime G double prime minus F prime F double prime G prime. M is 0, and N is F times G prime. Right? So using that, the first you will get, after you plug into the above formula, right? And that is going to be F prime double G prime and F. Okay? Then F G prime. So that is F squared. Okay. Now using the fact, okay, using the fact we actually using the fact F prime square plus G prime square equals 1. Using that fact, you can get rid of a G. Okay, so finally you will get F double prime F. Okay, so if you know F prime, so you can get G prime, right? G prime is going to be plus minus 1 minus F prime square. So if you can determine F, then you almost determine G. G is the integral of this square root, right? So G is going to be plus minus integral 1 minus F prime square du. Now, this is an interesting equation. Okay? You can also write it in the form, this is second order equation, ODE, ordinary differential equation. Okay? And the general solution, you can have as the following. Okay, so most interesting solution is F0 is 0 and F prime U equals 1. In that case, let me give you, okay, if you consider this initial condition, okay, then F of U is given by 2 formula, okay? That's going to be sine, I think that would be square root K, U when K is positive, okay? This will be just U when K equals 0. Yeah, and this will be parabolic sine square negative K, if K is negative. Okay, so you can write down, you can double check that, right? When you double check F double prime U, check. If K is positive, F double prime W is going to be negative square root K sine square root KU, right? And then it's going to be negative K, right? And this is again, it's F. Okay, so that's why it's indeed a satisfying equation. Okay, so we are interested in the surface of revolution with a constant curvature. Okay, let's in general, right? So general solution, I think, without the initial condition, I think the general solution will be 1 when K is positive, F of U equals A plus sine square KU, and the B cosine square KU, right? That's a general form. Okay. And you can also combine into one. I think will be like a square root of a square plus b square, and the sine hyperbolic of u, and plus another angle, right? That is another way to describe the solution. Okay, when k equals 0, f of u equals au plus b, I think. Yeah, when you differentiate twice, it's going to be 0. So the second derivative is 0, then it must be a linear form. That's a trivial case. When k is negative, f of u is the general solution a, hyperbolic sine square root of negative square root of negative k u, and b hyperbolic cosine. Okay. So this is a general solution. I think one can also combine into one. Okay, so let's keep it the general form, because this is a general form. Okay, and you can verify double the differential twice. In this case, it is going to be negative kf, right? Yeah, you can double check that. K negative k times f. So then move together. This is indeed a solution. Okay, so those are the general solution. Now, using this, using any of that, you can. So so we get following proposition. Okay. The following proposition is the surface of revolution has constant Gaussian curvature. Okay. If and only if, right? We completely determine. So this surface solution is a patches, right? Using the above patch, f of u cosine v, right? F of u sine v and g of u, right? Okay. If and only if f is given by the following, okay? F double prime u plus k f of u equals 0, and the g of u is going to be integral of plus minus square 1 minus f coming. Right? We don't specify the interval for variable u. Now let's take a look at a special case, some special case. The special cases. Yeah, the special case is case 1, k equals 1. Now, k equals 1, we know that it's f of u is going to be, in this case, since k is 1, right? Yeah, the square root k is going to be also 1. Okay. F of u, I just choose sine sine of u. Now, the solution, right? The general solution would be some number times some u plus theta. But I can choose this special one, okay? And this is indeed a solution, right? Yeah, okay. When k equals 1, differentiate twice. Right, so g of u is the integral of, yeah. So you can assume it is cosine u, right? Because then the derivative is going to be 1. So g of u can be assumed just cosine u. Okay, so those are the just special solutions. In this case, okay, what do we get? Sigma uv is going to be sine u cosine v, sine u sine v, okay, so, and then cosine u. This is just a sphere coordinate system for the sphere. Okay, what you get here is cosine. What is u here? U actually is from 0 to, yeah, u is from 0 to pi. Okay, and this is a u. Okay, and this is the angle theta, angle v. You project it here, so you get a complete sphere. Okay, so it is the unit sphere. Now, so what happens if we choose fu to be another constant? Let's call it r sine u, right? So this is also satisfying this equation, right? It's independent. So in this case, g of u is going to be integral square root of 1 minus r square cosine square u du. Okay? When you differentiate the f, you get cosine u. It's harder to evaluate, yeah. So you can use a maple to draw the picture, okay? And then sigma uv is going to be r is a constant, sine u cosine v, r sine u sine v. And then this is the integral 1 minus r square cosine square u du. How does this kind of surface look like? It has constant curvature. Yeah, it has constant curvature. But we cannot use the elementary function. It has constant curvature 1. Right? Yeah. So it'd be interesting if we can draw it in the space. Okay. But definitely this is a surface solution, right? When u is 0, this is going to be 0, this is going to be 0. Okay. So we are here. Okay. When the u increases, we just don't know the height where it is. Okay. So And clearly R cannot be, if I is too large, so we can assume that I is less than, I is less than or equal to 1. Otherwise, U is not defined. U cannot be from 0 to pi. Right? So we draw the picture like that. If I is less than, it's like a foldable type of surface, okay, with a singularity. Okay, that's the two singular point here. The Gaussian curvature is still going to be 1. Okay. Right. Yeah. If a story I is less than 1, so you have a family of a surfaces of revolution. Okay, it has constant curvature +1, but with a two singular point. When U equals 0 and only when it's around the sphere, one can see that it's a smooth everywhere. Okay, so this surface has constant curvature 1. Okay, it's harder to draw the curve in our best. Yeah, okay. Okay. All right, so now let's take a look at the negative case. Okay, no, the zero case. Yeah, the zero case. Okay. The zero case will be, it's easy to see. Okay. Right. Now, remember f of u is going to be is constant au plus b. In this case, I have to assume that since this square plus g prime u square is going to be 1, right? So here, a square cannot be larger than 1. Okay, right? So the trivial case here, we assume that a absolute is less than 1. Okay, and I can find out GU. So the plus minus square root of 1 minus f prime it's a square du, right? Plus constant c. Okay. Now, what do we get? We get a cylinder, and I think we can get cylinder and the cone. Okay, that's two types. Okay. So if a is not going to be 0, now what do we see? Okay, sigma u and the v, right? It's going to be au plus b cosine v, au plus b sine v, and here's plus minus. Okay, and actually this looks like a cone. Okay. Okay. It looks like a cone type. Now if a is 0, if a is 0, then this is cylinder, the special one, circular cylinder. When A is 0, and then sigma UV is going to be B cosine V, B sine V, N plus minus U plus C. Okay, so this is a circular cylinder, okay, with radius R, B. Okay, it is a circular cylinder. Right. Circular cylinder has constant curvature 0, and this is also has constant. Now, why the cone has constant curvature 0? Okay, if it's cone, okay, if it's cone, circular cone, what they do is they open this side, then you get a sector, flat sector. Okay, so you open and you get a flat sector. This flat sector, you know, curvature 0. But this procedure, when you open the cone, this procedure, what does not change is the distance between 2 points on the cone. Okay, so those two, you did the exercise, right? You can find the surface patches for this flat plane and this cone, and so that their first fundamental form are identical, the same. Right. This is their assumption. Okay, the map is an assumption. So the curvature here is 0. The curvature here is also 0. There's a reason, you know, when you modify, when you open a surface and make it flat, if this procedure does not change the distance between 2 points on the surface, then the Gaussian curvature will be not changed. And that's the idea. Okay. Think about our universe. Okay. Our universe 3-dimensional space, embedding in the 4-dimensional space, maybe even high dimension. You can also find a similar, you know, first fundamental form, second fundamental form. The second fundamental form tells you how curved is of our universe in the high dimensional space. But you are not a God, you cannot see it, okay? Because you cannot leave the universe 3-dimensional space. What you can figure out, just like Albert Einstein is a genius guy, right? You know, yeah, I'm surprised, you know, we have Einstein. Okay. So use based on the distance between 2 points in the universe, Einstein concludes that the universe is curved, but nobody else can see it, only him, okay, at that moment. All right, and so if our universe, when time changes, the universal changes, okay? So the God maybe see that our universe is gradually bend, you know, more curved in the high dimension space, but we cannot see that, human being. We can only detect the distance between you and me, or between 2 stars. We find out no difference. So we find, we can calculate the curvature of our universe, find out the universe, the curvature never be changed. So we cannot, if the curvature, no, there's a possibility the curvature also change when the universe changes. But also there's a possibility the curvature is not changing, so we cannot detect the change of the universe. And what's inside the universe? Clear? Yeah. And so if we cannot detect it, that means the curvature will still the same. Okay? The Gaussian curvature will be the same. Okay? So look at the cone, you know, in dimension 2, the surface. Okay, the cone, you open it, you cut along one line, you open this whole procedure. Imagine like it changes the universe, right? You are in 3-dimensional space, you can see it. yeah, you can see it, it's changing, but because you just simply you are in three-dimensional space. So there is a bacteria or ant on this core. And if they cannot see the ambient space, then what they can see is only the distance between 2 points. They find there's nothing being changed. This whole procedure, okay? There's nothing being changed. Suppose they use their eyes are covered. They can only use their feet, okay, to measure the space, the plane, right? They cannot tell the difference. When they open the eyes, wow, if you can see the ambient space, wow, now we are on the flat piece of paper, okay? Instead on the cone, cone is curved in something, you see? So the Gauss curvature, Gauss is very genius guy too, right? So he said that the Gauss curvature, which is product of the two principal curvature, okay? And depends on the first fundamental form, okay? So if the first fundamental form is not being changed, the whole procedure, and you don't, if there's a Gauss curvature, will not change, okay? All right, so now let's look at, I'm very interested in the negative curve, negative curved space. Yeah, negative curved space, okay? At least I want to find an example. Negative curved space can be constructed in a three-dimensional space, okay? Similarly, maybe negative curved three-dimensional universe can be constructed in a high-dimensional space. Okay, you can see it. All right, so k equals -1. Let me show you a special. I'm just interested in special solution. So I'm going to only consider a special solution. Okay, f of u equals e to the u. Okay, the general solution will be e to the negative u also has a solution. Okay, so clearly f double prime u minus f, right, minus because k is, right, k is -1. Okay, it satisfies this equation. Okay, so let's take a look at g. G is the integral of 1 minus e to u, right, in du. I think we can evaluate. It's good exercise in calculus. Okay, you can evaluate and minus natural log e to the negative u plus e to the negative 2u plus 1, great. And the plus constant, so we forget the constant. Okay, and the u is I think our u should be less than, yeah, what is the restriction on u? Because f prime u squared should be less than 1. So u cannot be positive, u is going to be negative if you use this one. So this u is going to be, if you use positive, this is not defined in square root of 1 minus e to the 2u, right? So u must be less than 0. Okay. All right. Wow. So we have a very specific function. Then sigma uv, right? And e to the u cosine v, e to the u sine sine v, and then okay, this one u is less than or equal to 0, and the v can be, can be any. Yeah, so you get a complete circle. Okay, this surface, okay, it's harder to draw it, And the radius depends on the value of e to the u, right? So think about this. This is going to be x, z, y-axis. When u equals 0, when u equals 0, when u equals 0, my starting point, right? F of 0 equals 1. And what is the g? The g value. When u equals 0, this term is a 1, natural log 1 plus 1 plus 1. So it's a number, right? It's a negative number. So that means when u equals 0, the starting point is x is going to be 1, right? So z value is going to be negative. So somewhere here, okay? Now, when u goes to negative infinity, where's u equals 0? When u goes to negative infinity, you get a curve. So f of u is going to be, f of u is actually the radius, right? So for the surface of a revolution. Okay, so f of u is the radius. So this direction, u approaches negative infinity. Okay, so the radius is getting smaller and smaller. And I think g of u approaches negative infinity. U approaches negative infinity, and g of u and clearly approaches negative infinity. Right. Now we can in the z plane, right? We know that x in the xz plane, we know x is going to be f of u, right? E to the u, and z is going to be we already calculated this. Z is going to be square root of 1 minus e to u minus natural e to the negative u plus e to the negative 2u plus 1. Okay. So we can eliminate the variable u to get an equation between x and z. Okay. So z, this actually, we know that, we also know that hyperbolic cosine t is going to be natural log of t plus square root of t squared and plus 1. Right? Yeah. We're using this fact. We're going to simplify the notation. So z, yeah, z is going to be square root of 1 minus e to 2u is going to be e to x squared minus natural log of, this is hyperbolic cosine, right? Hyperbolic, inverse hyperbolic cosine. Okay, so this is just 1 of x. So here, x is e to the u is less than, so x is actually, x is going to be between 0 and 1. Okay. And z is going to be, when x approaches 0, z approaches, when x approaches 0 from positive side, z approaches negative infinity. Okay. Okay, now we have yeah, that's what we have, right? We have a curve in the XZ plane, completely determined by this equation, and then you rotate this curve around the z-axis, and you get a surface. This surface has constant curvature -1, and it goes to infinity. Right. Yeah, this is it's interesting surface. Yeah, right. I'm going to describe this surface U and the V as a sigma. Okay. And the V, it's a 2 pi from 2 pi to 0 z now. U is going to be, I think U is going to be negative, right? So this is a whole region. And what we did here actually is that this map is like that. These two glued together, okay, and the left. Okay. So you get some kind of a cylinder glued together, right? This line and this both line will be sent to this ladder line, this ladder line will be here. Okay, just you rotate clockwise 90 degrees and close it, make a loop, make a cylinder that's getting smaller and smaller when you go to negative infinity. Okay, so that is a picture. I'm going to construct another. Okay, so this is the first fundamental form. Let's go back to the first fundamental form. How does it look like? The first fundamental form, right? E is going to be 1, F is going to be 0. G, I remember, right? G is going to be F squared. Right? So that's the first fundamental form. And this clearly approaches 0 as U approaches negative infinity, right? Okay. I'm going to define another map. Okay. So this is this will be the W. This will be V. So the map goes like that. I want to construct another one, right? I want to construct from here to here. This is sigma 2. Okay. V is not changed, the W is changed. So the relationship between W and V is from here to here Okay. U equals U equals negative natural log of W, about like that. Okay. U is going, W is going to be, U is going to be less than, yeah, in other words, W is going to e to the negative U, right? So if U is less than or equal to 0, W is greater than or equal to 1. When U goes to infinity, let me check. W, U less than or equal to 0 implies negative U greater than or equal to 0 implies W equals e to negative U greater than or equal to 1. Okay. When U goes to negative infinity, W goes to positive. Okay. So what I got here is this region. Okay, flip it over to that. So I get a map. Okay, W is greater than 1. Okay. And then I construct sigma U WV. Okay. Which is going to be, U is going to be e to the right. Okay. So e to the U is 1 over W. So 1 over W cosine V, 1 over W sine V. Okay. And what else? So G of U is also will be changed to G of W. Okay, so that will be 1 minus 1 over W squared minus hyperbolic cosine W. Okay. Okay. So here W is greater than 1, V is between 0 and 2 pi. All right, so be careful about this. So what is the second fundamental? What is the first fundamental form of this? The first fundamental form of this was, yeah, you can get the fundamental form, right? So we know that it's going to be du squared plus, at the very beginning, we have this, right? Let me check. Yeah, F is e to the U. So it's e to the 2U dV squared, right? So now, according to our computation, I'm going to change the du to, you can transfer, you can change the first one of them using directly, okay? You don't need to repeatedly do the computation for this. Okay, dw equals negative e to negative du, okay? So that means du equals negative e to the u dw, okay? So du squared is going to be e to the 2u dw. Okay, so this is a constant. Okay. Now e to the u, I have to change it to the w. E to the u, okay. Look at e, yeah, w is going to be e to the negative u, right? So e to the u equals 1 over w, right? So it's square, so it'll be w squared. Okay, so in other words, you construct the map. You construct the map. This is W, and the VW is greater than 1, right? Onto this surface in the space. Okay, right? Such that the first fundamental form in this simple form. Okay, it is going to be conformal, and you get this sigma. This sigma 2 is a conformal matrix, right? Do you agree? Yeah. Okay. So this, you know, WV is a flat plane. Okay. So you can because this is just constant times d. So sigma 2 actually is a conformal matrix. Okay. It does not preserve the decimal, but preserve the angles. So sigma 2 is actually going to be R2 to the surface. Okay. So this is a conformal mapping. Okay, it's interesting, right? After you modify. Okay. And when that, yeah, so when along this circle, W is going to be 0. When W goes to infinity, this, right? W goes to infinity. Okay. Yeah. So the picture looks like this. This line, this line, this line, and again. Red line, red line, red line, red line. Okay. Now further, if you modify you can also change the variables. Okay, U and V, W and V right now, you can change it to the variables. Then this first fundamental form will be also changed. Okay, I think this is the most interesting case. Right, this is just a surface patch. It's a different surface patch. We have two different surface patch here, right? And the first one is coming from the surface erosion. It's very natural. Right? But for that surface patch, the first fundamental form does not look good. Okay, the coefficients here. Okay, yeah, there's a coefficient here. Now this becomes simpler. Let me briefly talk about another example. If we consider the surface, the graph, right? This is a parabola. This is actually a special surface of a revolution, right? Do you agree? Right? And but this is a curve in the in the xz plane. But I do not use a unit space curve. The curve here. Yeah, this can be described as surface revolution. But be careful. You have to reparameterize it in order to get curve, right? So gamma u is going to be u, and the 0, z is going to be u squared. Okay, but this is not going to be you need to split the curve. Okay, so one of the possible parameterization is going to be, so for each point, right, x, the corresponding value z, right? When you can set y to be 0, so we x squared. So this will be u cosine v, u sine v, and the u squared. Okay, you can use this parameterization to find this surface patch to find the EFG. Okay. So let's see. So we use our f is going to be u can use square. Okay. We can get e equals 1, f equals 0, g equals u squared. M is going to be f prime, by f prime and g double prime minus f prime e double prime. Okay, and that is going to be f prime is just 1, g prime is 2u, right? Minus f double prime is 0, so this is just 2u. Okay. This is m. Now this is L. Okay. M is going to be 0. N is going to be f g prime. So f is u, g prime is 2u. So 2u squared. Okay. So the Gauss curvature is Ln minus m squared EF minus EG minus F squared. Okay, let's put them together. Okay, Ln 2u squared. M is 0, EF u squared. EG minus F squared. Yes. Okay. So that is going to be negative. Wait a minute. Did we N, okay, N, LMN, 2U squared. Yeah, I'm not sure this is we use did we use a condition or not? Okay, because this is not a unit speed. It's not a unit speed curve. Okay, so if you use that formula without the check the condition, what you get here is going to be twice of u, right? Okay. All right, let me, I think here we cannot use this formula because the curvature I got here is, it goes to infinity, right? When u goes to infinity. So it's clearly, you cannot just use the formula given in the book because this formula is true when f prime square plus g prime square is going to be 1, okay? Now, so here, if you just quote the theorem without the checks the condition, okay? Yeah, this f prime u square plus g prime u square is not going to be 1, okay? So if you use that formula, you end up with a 2u, which is not the Gaussian curvature. Now, what we can get for the Gaussian curvature is we still use the original function, okay? X, Y, it's x squared as a graph, okay? And this is your exercise. You compute it. It's going to be 1 plus f prime square, fy prime y prime square, okay? That's a square, and here the second derivative, okay? Then you will see when, you know, the paraboloid, right? Paraboloid is more flat nearby infinity. So the second derivative is going to be 2, and the second derivative with respect to y is 2, and that is going to be 0. Okay, 1 plus the first derivative is 2x squared, is 2y squared, and the square. Now it's going to be 4 here, okay? And the 1 plus 4x squared plus 4y squared and the square. And that is the correct formula. So clearly when it approaches, when this goes to infinity, okay? So when x squared plus y squared approaches infinity, then curvature approaches 0. And then look at the parabola, right? Paraboloid, right? And you look at this picture. Clearly, it's more flat nearby the infinity. So k approaches 0. It's not a surprise. The Gaussian curvature, okay, and getting far away from the origin, okay. So here, this formula is wrong, okay. The reason is we used formula for the we use this formula, okay. This is a wrong formula, okay, because this is true under assumption when f prime square plus g prime square equals 1, okay. So be careful when you do the homework, right? Just say calculate the curvature, Gaussian curvature of this paraboloid. Now, if you view this as a parameterization, if you view this as a surface erosion, then you have to make sure, if you want to use a formula in the book, you have to make sure the curve you're going to construct has a unit speed. Otherwise, some terms are missing, okay? So you will get a Gaussian curvature, and this looks like it approaches infinity. When you approaches infinity, that's clearly is not true. Okay, and the paraboloid actually become more and more flat. Gaussian curvature should approach zero. Okay, so let's stop here and make sure you submit the homework before next Monday. Okay.